Hello, my name is Bernhard Brandstetter from Virtual Vehicle Research in Graz. Together with the coordinator Volvo Cars, I have been responsible for the project advice and its results. And I have the honor and the pleasure to present them to you within the next couple of minutes. The overarching long-time target is to increase the number of hybrid vehicles on the roads and thus contributing to the European CO2 targets. Conventional premium class vehicles have problems in reaching the environmental targets, and this is why we are targeting them in the project. We started with the project 3.5 years ago with a funding of 10 million euros from the European Commission. Volvo Cars coordinate the project, while we at Virtual Vehicle have been in charge of overall project management. We had 20 partners reaching from car makers over tier 1 suppliers, RTOs, and academic partners. In advice, we wanted to cover different widely used hybrid architectures ranging from mild hybrid over full hybrid to plug-in hybrid, taking advantage of exploiting the possibility to downsize the internal combustion engines. The mild hybrid was set up with a starter generator machine and an electrical axle in the rear. The HEV has an e-axle in the rear as well, but the main feature is the high power 400-volt battery. The plug-in hybrid has a so-called P2 system acting on the rear, while an all-wheel drive has been investigated with 2 electrical machines acting on the front axle via an e-twinster system from the project partner GKN. The cost target was to achieve a cost premium of 5% for mild and full hybrids and 15% for plug-in hybrids compared to the best-in-class non-hybrid diesel vehicles available on the market. Another important selling argument for the vehicle class under consideration is the vehicle performance and fun to drive. For this reason, a cost assessment procedure was set up to take into account total cost of ownership and a cost-benefit analysis. Of course, the decrease in fuel consumption is a main driver for hybrid vehicles. To achieve this, besides the obvious engine downsizing, we take advantage of predictive control strategies and eco-routing, eco-driving functionalities. To get down the emissions optimized after treatment with electrically heated catalysts and engine strategies in hybrid mode are exploited. Here you see at a glance the vehicles that have been hybridized in advice. The HEV and the PHEV demonstrators with gasoline engines, while the 48-volt demonstrator is running on diesel. For the HEV demonstrator, a high-power battery with a new cooling concept and laser welding technologies from Fraunhofer ILT was developed, showing high potential to be implemented in a modular way in different platforms. The 48-volt motor and battery pack by AVL was integrated in the P4 e-axle of the 48-volt demonstrator. For drive performance and efficiency, the GKN e-twinster architecture has been evaluated with following advantages. Regenerative braking improves the efficiency of the system, as can be seen in the right diagram. Red is without regeneration and black is with regenerative braking. The system offers up to 80% of the electric drive torque to improve the lateral dynamics of the vehicle with the torque vectoring. In the middle, the results show that the critical speed, which is the maximum speed at which the test can be performed successfully, is increased by 8.3% thanks to the implemented torque vectoring system. At Virtual Vehicle Research, we examined a heat storage with 3 kg paraffin. We validated the characteristics on the testbed and assessed it on vehicle level via simulation, leading to a faster heat up of the battery and keeping engine temperature on a more constant level with the potential to increase noxious emissions. Co-simulation played an important role to optimize and assess innovations on component and system level, and to demonstrate the potentials of predictive controls. Eco-routing, which is finding the most energy-efficient route, is more complex for hybrid systems than for conventional vehicles or fully electric vehicles, since hybrid vehicles offer more degrees of freedom. Eco-driving requires a validated model of the vehicle and its components to guide the driver towards the best way how to drive the eco-route. In advice, we interact with the driver via an HMI, giving information about eco-routes and the best way to drive. A controller for the electrically heated catalyst was developed that, due to the high temperature semiconductors used, can be placed close to an electrical heated catalyst. We have finished our evaluation of performance, emissions, and energy consumption on testbed and under real driving conditions, partly assisted with our validated co-simulation environment. Here you can see two different routes that have been chosen to validate the vehicles under real driving simulations. Eco-routing was evaluated along two different routes in Aachen. We have compared the fastest route consulting from typical navigation systems versus the most energy efficient route, resulting in a significant reduction in fuel consumption. We have evaluated our demonstrators comparing WLTC versus real driving results taken at the routes in Spain shown before. For the 48-volt demonstrator, we have used a validated co-simulation calibrated along baseline vehicles and component and subsystem measurements. Due to the confidentiality issue, I'm not allowed to show you numbers, but only a color table showing that the targets have been achieved. In the case of the HEV demonstrator, the calibration of the vehicle could not be optimized due to COVID-19 travel restrictions. But the involved partners are sure that based on the evaluation results, the target can easily be achieved after calibration. The efficiency and the fuel consumption of the PHEV demonstrator have been much better than the target. For the emissions, all the targets with respect to Euro 6D could be achieved. For drivability, the HEV demonstrator showed excellent results. The torque vectoring for the PHEV demonstrator has been shown before, proving the potential for drivability. The 48-volt demonstrator could not be tested before the project end due to travel restrictions, as mentioned before. For evaluating the cost target, we have compared the retail price, the total cost of ownership, and made a cost-benefit analysis where efficiency, emissions, and performance resulting from the tests have been considered. The evaluation was made against the best-in-class diesel vehicles on the market. The cost assessed for all vehicles is in line with the targets. As a summary, the advice project was a big success for all involved partners who could take advantage of the different developments, and all partners reported possibilities to exploit these results in the near future. Thank you for the attention, and I'm open to your questions.